In this video, we're going to talk about one of the more important things in physics, the principle of superposition, which leads to discussions about wave interference. So to see what we're talking about here, I want you to imagine that we'll deal with the orange wave in a second. Imagine that the green wave and this sort of purplish wave are the same kind of wave, and that they are traveling through the same medium at the same time. Now, I haven't said what kind of wave they are. It could be any kind of wave, because what we're talking about is a property of all waves. But we're going to assume that they're the same kind of wave, traveling through the same medium at the same time. For purposes of clarity, I have given them the same wavelength. And if they're the same kind of wave in the same medium, that means they have the same frequency, right? Because the same kinds of waves will travel at the same speed. And the speed of a wave is related to the frequency and the wavelength. So if they're the same kind of wave, they have the same speed, in the same medium, I should say. And they have the same wavelength, which means they'll have the same frequency. Okay, now they don't have, what we're going to talk about involves all kinds of waves, and so they certainly don't have to have the same wavelength and frequency to exhibit this behavior that we're going to talk about, but just for ease of drawing, I've given you that. So if you notice, what I have done is I've lined up the peaks and the troughs. If this wave is coming from a source, we would say that the sources are in phase, and we say that the waves are in phase. For instance, if this is if these waves are coming from speakers, if they're sound waves, both of the speakers are firing in sync like this. Whatever is producing these waves, the motion has been coupled up, and the waves are exactly the same wavelength and exactly the same frequency. I have given them a different amplitude, right? Here's some amplitude, we'll call that A2 since it's the second one. And this one would be A1 since it's the first one. But what happens when these waves are traveling through the same medium is that if these are mechanical waves, they are displacing the medium. If they're not mechanical waves, if they're EM waves, they're not displacing the medium, but they still have amplitudes. And when these waves overlap in this manner, that is where the peaks line up and the troughs line up, we see that the amplitudes will add together. Again, if this is a mechanical wave, whatever is oscillating, whatever is displacing, the displacement will be the maximum displacement, I should say, will be the sum of the amplitudes. In the case of an EM wave, if this is the electric field component, you would have an amplitude of the resultant wave that's A1 plus A2. What I'm saying is that these waves will produce a single wave, which will look kind of like this, where this amplitude is equal to A2, I grabbed the wrong color, so I wrote the second one first, A1 plus A2 is this amplitude. Now, I haven't drawn it particularly well because I was trying to draw it bigger, but the idea, these waves will add together in such a way that the amplitudes of the waves add together. Again, if this is a mechanical wave and there's some sort of medium, the wave will just be, the displacements of the medium as these waves pass by will just be bigger than A1 or A2. They're going to be A1 plus A2. This is why two people shouting is louder than one person shouting, right? The amplitudes of the waves are going to add together in interesting ways. This is one way they could do it. We call this constructive interference. I'll write that down here. I'll write it in blue since that's what I did. Constructive interference. All right, so that's what happens when I add A1 and A2 together. What about this orange wave? I'll call that A3. what about if I forget about the green wave now? What if the orange wave and this lavender wave are traveling through the same medium at the same time? And they're the same kind of waves. Well, you notice that the orange wave has been shifted with respect to the lavender wave. It is out of phase. In fact, we would say it's 180 degrees out of phase. It's been shifted over by a certain amount so that I've lined up the peaks here with the troughs here. I've lined up this peak and this trough and this peak and this trough. So when these waves pass through a medium, they produce a resultant wave which has an amplitude less than each of these waves because the amplitudes are now adding together negatively at every point. And so what do I get there? I get a wave that looks something maybe like this. It's going to kind of depend on which wave is bigger. But I get a wave that looks something like this. If A2 and A3 have exactly the same amplitude, they will cancel out completely. In fact, that's how noise canceling headphones work, which many of you I'm sure have. But the idea is these things add together. In this case, in the case of the lavender and orange wave, we would call that destructive interference. So just because we use the term interference for both of them, interference is not necessarily a bad thing, but constructive interference will add the amplitudes of the wave together. Destructive interference will subtract the smaller from the larger. In the case where they're both of the same amplitude, could cancel out the wave altogether. And we'll see both of those examples a little bit later. Together, this idea is called the principle of superposition. The idea that two waves of the same type can travel through the same medium at the same time and interfere with each other in interesting ways. So that whole idea is the principle of superposition. This is how that works out practically. We get either constructive or destructive interference. Now, of course, I've lined these waves up really nicely so that they're all the same wavelength, same frequency. I, of course, don't have to do that. We'll look at that in a second. But first of all, I want to talk about, I'm going to move this over, how I got the orange wave shifted. If this wave is coming from some sort of source, maybe I should say if this one is coming from some source, and this wave is coming from an identical source, but what I've done physically is I've moved the source back. How far back did I move it in order to get this complete, or to get this destructive interference? If the source was over here along with the source of the lavender wave, I would expect them to be in phase. But if I move this source back a certain distance, all of a sudden they are out of phase. Of course, there are intermediate steps. I could move it back a little bit and they'd be a little bit out of phase. Move it back some more, they'd be a little more out of phase. When I move it to here, they're completely out of phase. How far back did I move it? Well, it looks like I moved it back this much, right? Okay, that's fair. I moved it back this much. What does that mean? Well, notice I've moved it back by half of a wavelength. So if I shift this wave by half of a wavelength, what I do is I make what was constructive interference into destructive interference. And again, there's some intermediate cases. I could move it like by lambda over 4, and I kind of cancel out some places and add together in other places. But if I move it by half of the wavelength, if they have identical wavelengths, I should say, if I shift this over by half a wavelength, I get destructive interference. I could, of course, keep shifting it. What would happen if I shifted it over another half of a wavelength? Well, that would mean that this point would be shifted over to this point. But if you compare what's happening here to what's happening here, notice I would get back the constructive interference. So if I shift, let me say, half integer multiple shifts, that's lambda over 2, 3 lambda over 2. 5 lambda over 2. They give me destructive integer multiple shifts give me back constructive. What are my integer multiples? If I don't shift it at all, I get constructive. If I shift it by 1 entire wavelength, I get constructive. If I shift it by 2 entire, move that over to C. If I shift it by 2 entire wavelengths, I get constructive back. So half integer multiple shifts of my waves, or of one wave, gets me destructive interference. Integer multiple shifts gets me constructive interference. All right, so let's look at a case where the waves aren't so lined up. If I have different wavelengths. So I'm going to put both of these on the same axis. Let me get the axis in blue. So my first wave, I'll say will look like that. And my second wave, I'm going to give a different wavelength. Something like that. So again, if these are propagating through the same medium at the same time, they're going to interfere with each other. To see how it works out, let me just divide up some regions. I'm going to figure out when my waves are both positive or both negative, or one positive and one negative, and kind of mark those off. Looks like there's a region there where one is negative, one is positive. And then I get this region where both are positive, and then I get this region where one is negative again, and then it looks like they're both positive, and then both negative, and you see, so on and so forth. All right, well, let's say this is region 1, 2, 3, 4, 5. I could go on, but I think you get the point. In region 1, it looks like I've got a negative contribution here and a positive contribution here, so this is going to be destructive interference. In region 2, looks like I've got a positive contribution from both. So that's going to be constructive. That's not how you spell constructive. And in region 3, my lavender wave has gone negative again. Looks like I'm going to get destructive there. And you see what's going on. 4, I'm going to get constructive. I'm going to look at 5, actually. In region 5, they are both negative, and so you might tend to think this is destructive, but destructive occurs when one is positive and one is negative. If they're both negative, notice they will have a larger amplitude than either one of the constituent waves in that region. It's a negative amplitude, but so what? So region 5, where they're both negative, is also constructive interference. Constructive interference occurs when both waves are either positive or negative. Destructive occurs when one wave is positive and the other is negative. Now, you might ask, well, what does this resultant wave look like? And I will do my best to draw it, but it's going to be terrible because this is actually not that easy to draw. A computer could do it pretty well, but I will do my best just to show you sort of the funkiness. And so in this one, it looks like it's going to start out maybe going negative, because it looks like the lavender wave has a steeper curve than the orange wave. So it looks like we start out going negative, but then somewhere halfway in the region, when I start trending upwards here, my net contribution is probably going to end up being positive. So in region 1, I'm going to get something like this. And then region 2, they're both adding together, so it goes up steeply at first and then kind of squares off as this bends over and then falls back down. But it looks like it doesn't go negative. It looks like in region 3, the orange is still winning, so I'm going to stay positive. And then in region 4, they're both positive, but it starts to come down. And then finally, going into region 5, it's negative, and I get a steep slope here. And then looks like for a little bit in this next region, actually looks like in the whole region it's going to be negative, but trending upwards here and then trending back down here. And then in this one, they're both negative, so it's going to go down. And then here, it looks like I'm still negative, but trending upwards. And then here, I'm still negative. And finally, over here, I come back positive. So I get something that looks like this. Now, is this accurate? Well, probably not. But you get the idea. So this is, if you ever have seen sound waves, like, a wave representation of, say, a trumpet or a clarinet, or even somebody speaking, it doesn't look like a sine wave or a cosine wave. It looks like this. And that's why. It's because in the normal everyday sounds, like a speaking voice or a trumpet or a guitar, consists of lots of different constituent sounds that are adding together and producing a wave with a very unique shape. This is actually, this unique shape is what gives different voices their different characteristics. It's what makes you able to distinguish a trumpet from an electric guitar, or distinguish one of your friend's voices from one of your other friend's voices. Even if they're talking at the same time, you can tell the difference. The shape of this wave contributes to what a musician would call the timbre of the sound quality that makes it distinctive. Your ear is able, interestingly enough, to hear this sound wave and immediately divide it up into its constituent parts. In other words, if you have two friends talking to you at the same time, you can tell their voices apart. Your ear is able to pick up this, which is what is actually reaching it, and decompose it into the constituent waves. That's actually really difficult. Mathematically, we have to do what's called a Fourier transform to get from here back to here. It's easy to look at this and get here. Not easy to look at this and get here. But your ear does it immediately. Your eyes don't, right? Yellow and blue make green. We all know that. So when you look at green, this is green. Do your eyes see yellow and blue together? They don't. They are unable to separate light waves into their constituent colors. The waves that blend together in interesting fashions to form different colors. Your eye can't separate that, but your ear separates it immediately. I just kind of find that interesting. All right, we will look at more interference in the next video.